Okay, this is exam 4 for physics 102, 2M, the 2M section. It says a mirror produces an upright image. The object is 2 centimeters high. The image is 8 centimeters high. The center of curvature of the mirror is 16 centimeters. Where is the object located? The first thing I want to know is what type of mirror this is. I know that it's producing an upright image, and it appears the object is 2 centimeters high, the image is 8 centimeters high, so my magnification is equal to positive 4. The only mirror that will produce a bigger upright image is a concave mirror, so I know that this is a concave mirror, and that the center of curvature is 16 centimeters. That tells me the focal length is half that, or 8 centimeters, and since it's concave, it has a positive focal length. All right, where is the object located? Let's see, so I know that this is 4 is equal to negative q over p, and I know that 1 over 8 equals 1 over q plus 1 over p, and I want to know where is the object located, so I want to know what is p. So I'm going to say then, I'm going to solve this and say q equals negative 4p. I'm going to take this and put it in here for q. So I get 1 over 8 equals negative 1 over 4p plus, I'm going to go ahead and make this a 4 over 4p. So that's 1 over 8 equals 3 over 4p. And I solve this, I cross multiply or do whatever you want to do. 4p equals 24, so p is equal to 6. So the answer for this one is D. A convex mirror has a focal length of 10 centimeters. An object is 10 centimeters from the mirror. Where is the image located? All right, convex mirror has a negative focal point, so it's negative 10. And the object is 10 centimeters. I just want to know Q. Let's see, that's negative 2 over 10. Sorry. The inverse of negative 2 over 10, so that's equal to negative 10 over 2, are 5 centimeters. The image is located 5 centimeters from the mirror. Your makeup shaving mirror has a focal length of 20 centimeters. If you stand 40 centimeters in the front of the mirror, what is the magnification? All right, so the focal length is positive 20, p is equal to 40, and I want to know the magnification. This is 2 over 40 minus 1 over 40. So it's equal to 1 over 40. So Q is equal to 40. So M is equal to negative Q over P, which is going to be negative 40 over 40, or negative 1. But look, this is a concave mirror, and the focal point is here, and I'm standing here. I know that if this is my object, my image is going to be inverted. So it has to be C, because that's the only one with a negative focal point. Right. This shows an optical device and an image it creates. What kind of lens or mirror is this? Well, let's see. The image is a virtual image because it's upright. That tells me that it has to be a mirror, because virtual images are on the back side of mirrors. They're on the same side of the object as a lens, but for a mirror they're on the back side. And it's smaller. This is like a security mirror, so that's a convex mirror. So are the rays drawn for this concave mirror. Which ray is or are drawn incorrectly? Let's see, parallel to the axis and through the focal point. That one's correct. So it's not A. C. This one goes through C and then parallel to the axis. That is not correct. So what's that number? Number 2 is not correct. Now let's look at number... I'm sorry, hold on. All right, so this is number 3 actually. And it is correct. Parallel to the axis and through the focal point. This one is through the focal point and parallel to the axis. That's number 1. So number 1 and number 3 are okay. It's number 2 that's not right. So the answer is D for number 5. What kind of mirror produces a virtual image that is larger than the object? That is a concave mirror. If I'm inside the focal point, it's my object, it's my image. It's like a shaving mirror. So number 6 is B. Which of these rays is drawn incorrectly? Okay, so looks like it's just going to be ray number 1, because this ray, it should go through the focal point. The way this ray number 1 should look is that I should have a ray that comes up here and then it goes parallel to the axis through the focal point and parallel to the axis. But that's not how ray number 1 is drawn. Number 2 is correct, parallel to the axis and through the focal point, and number 3 is straight through the lens. So it's number 1 is the right answer, A. A convex lens can produce which of these? Remember, a convex lens looks like this. It can produce a virtual image, it can produce a real image, it can produce a magnified image, and it can produce an upright image. So E is the right answer for number 8. Convex lens has a focal length of 30 centimeters. Since it's convex, it looks like this. This is positive 30 is F. An object is 60 centimeters from the lens. What is the magnification? All right, well, Q is 1 over F minus 1 over P to the negative 1. So that's 1 over 30. That's 2 over 60 minus 1 over 60 to the negative 1. That's equal to 60. So Q is 60. I want to know the magnification. Negative Q over P, negative 60 over 60. Oh, it's negative 1 again. And look, this is just like our previous problem. So if I think about this convex lens, its focal length is 30 centimeters, and I have the object outside the lens. That means that the image is going to be inverted. That's going to be negative. Farsightedness is corrected with a convex lens. What type of device is this? A convex lens looks like this. It causes rays to converge, so it's a converging device. A person uses a converging lens that has a focal length of 10 centimeters. F is equal to 10. The lens forms a virtual image 20 centimeters away. So Q is equal to negative 20. What is the magnification? All right, so P here is 1 over F minus 1 over Q to the negative 1. That's 1 over 10 minus 1 over negative 20 to the negative 1. That is 20 over 3. All right, and I want to know what is my magnification. This is P, negative Q over P, negative 20 over 20 over 3. These cancel, leaving me with positive 3. So 3 is the right answer for number 11. Consider this two-lens system. What is the final magnification? Okay, well, this is P1. I find Q1 is 1 over F minus 1 over P to the negative 1. That's 1 over 10 minus 1 over 20. That's 2 over 20 minus 1 over 20 to the minus 1. That's equal to 20. So, and then also M1 is negative Q1 over P1, which is negative 20 over 20. Is negative 1. So my first image is going to be 20 centimeters. It's going to be right here, where this distance is 20 centimeters. And then my second one, P2, will be 20 centimeters. So I can find Q2. One over 30 minus 1 over 20 to the negative 1. Now look here, my focal length is right here. So this object for this lens is inside the focal point, so my Q is going to be negative Q2. That'll come out, let's see, do a common denominator. This is 2 over 60 minus 3 over 60. That's equal to negative 60. And then my magnification, M2, am I looking for the magnification here? Yeah. M2 is negative Q2, which is negative 60, over P, which was 20, is positive 3. So my total magnification is negative 1 times positive 3. Well, let's see, to make a mistake here. Hold on, let me find it. I'll come back to this, find my mistake. Okay, no mistake, as just the answers aren't correct. So I will fix this. This should say -3, so the answer will be C, right? So that's number 12. All right, number 13. If Earth's atmosphere no longer existed, how would the sunset be affected? Sunset would occur earlier. Lenses experience which of these aberrations? Lenses experience spherical aberrations and chromatic aberrations, so C is the right answer. Camera can focus on different objects by changing the distance between the lens and film. When is this distance the largest? All right, so a camera uses a convex lens. There's my film. When something is really far away, the focal point is at the film. All right, if something is closer, there's my lens. I have to move my lens further away, so my focal point's there, in order to form an image at the film. So there I've just sort of sketched my light diagrams. This is my focal point when the image is close, when the object is close. This is my focal point where it has to be when the object is really far away. So the distance is the largest when the object is nearby. When two waves are offset by one wavelength, they experience total constructive interference. That would be like having two waves like this. This is one wavelength, and so the next wave would start here, and there the peaks would still line up with the peaks and the troughs with the troughs. These two waves are offset because they're traveling different path lengths. By what amount are they out of phase? All right, this is one wavelength, so this is a half a wavelength, so they're half a wavelength, so 180. D is 17. Two waves of wavelength 4 meters travel through space. The first wave travels 8 meters, the second travels 10 meters. 10 minus 8 is 2 meters, so I have a path length difference of 2 meters. That's half of 4 meters, so it's a half wavelength offset, so it's total destructive interference. In Young's double slit interference apparatus, by what factor is the distance between adjacent light and dark fringes changed when the separation between the slits is doubled? All right, d sine theta equals m lambda. If this is doubled and everything else remains the same, this has to be halved. So theta becomes half theta, and I know that y is equal to L tan theta. If theta is halved, then the distance between the slits is halved. So 19 is going to be B. All right, I have a Young's double slit apparatus. Screen of position is given. The distance is 1.42 centimeters. What is the light source wavelength? Okay, you sort of have to work backwards here. I know that y is equal to L tan theta, and I'm given y right here, and I'm giving L. So I say y is 1.42 centimeters, that's 0.0142 meters, equals 1.6 meters times tan of theta, and then I solve that for tangent of theta. That's going to be the inverse tan of 0.0142 divided by 1.6. That's 0.5 degrees, 0.5085 degrees. All right, so that's my theta, and now I come back to this d sine theta equals m lambda, and I'm looking the distance between between alternating bright fringes, so I'll just let m equal 1. I'm solving for lambda. D was given, that was 0.04 times 10 to the minus 3 times sine of that 0.5085. So I'll say 0.04 times 10 to the minus 3 times sine of 0.5085. I get 3.55 times 10 to the minus 7 for lambda. All right, so 355. So number 20 is C. This is a little bit different from what we've done before, but it's really just sort of working backwards. This figure shows a double slit diffraction pattern. What is the path length difference of the light rays that interfere to produce a designated bright fringe? Oh, actually, this should say dark fringe. I will change that on the test. The dark fringe here, let's see, this is a half, 1.5, 2.5, so it's 2.5 wavelengths for number 21. Single slit is used to create an interference pattern on a screen. If you increase the width of the slit, what happens to the width of the central bright fringe? We had this question, it gets narrower, but let me just show you. If I increase A, I know that A sine theta equals m lambda. If A goes up, theta has to go down, so it gets narrower. Diffraction gradient is 4,000 lines per centimeter. What is the slit separation? All right, so 4,000 lines per centimeter, that's going to be 1 over 4,000. That's equal to 0.0003. Wait, no, I'm sorry, 0.00025. All right, so I know it has to be either B or C. I just need to figure out which it is. Now this is in centimeters, so I'm going to move it over 2 spaces, 0.00, and then, so that's 2.5 microns. Or rather, yeah, 2.5 times 10 to the minus 6. C is the right answer. What is the highest order maximum for a wavelength that can be obtained with this grading? All right, so first of all, D is 600, 1 over 600 is 0.0017. That's in millimeters, so it's going to be 0.0000017 meters. That's my slit width, and my wavelength is 450 nanometers. So I say D sine theta equals m lambda. D is that value I'm looking for here for m. Remember, I let sine theta go to 1 because theta equals 90 degrees. D is this 0.000017 divided by lambda, which is 450 times 10 to the minus 9. I get 3.8. That means you see 3 orders. So B is number 24. And at what angle would the second order maximum occur for a wavelength of 400 nanometers using a diffraction gradient of 1,000 lines per centimeter? All right, so I'm probably going to take one of these out, but I'm going to go and work this out just for future sake. So I have D sine theta equals m lambda. I want to find D, that's 1 over 10,000. That's equal to convert that to meters, and now I'm looking for the angle. M lambda over D. I'm looking for the second order maximum, so that's 400 nanometers. Over D, which is 0.000001 meters. I'm taking the inverse sine of all this. And let's see, that gets me 53 degrees. What caused the diffraction pattern in this picture? We've had this question before. It was in the online test, or the quiz rather. And what is your favorite class? Oh, let's see, it's hard to choose, but I'm going to go with A. All right, that's the end. I might have some revisions from this for the actual test, but it'll be largely the same.